Okay, very good morning. I'm sharing the QR code. Give the attendance, then we will start. Give the QR code. Okay. So I think everybody has given the attendance, so we can start. Okay. So yesterday my voice is audible now. My voice is audible. Hello. 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 Is my voice audible?
Yes, ma'am.
Okay, okay. Asha, yesterday I have given you a problem. Have you done that? Have you done that problem? So anybody please read out that problem. Read out that problem, please. That one, a constant RMS voltage of frequency 3 megahertz. That one. Please read it out. If anybody is having have written the problem, read it out.
Yes, ma'am.
That's what read it out.
A constant RMS voltage of frequency 3 megahertz is applied to a coil of inductance L and resistance R. A calibrated variable capacitor C and thermojunction is in all series. The uncalibrated emitter is found to show the same scale reading I. For two values of C, 37 picofarad and 45 picofarad. One being below and other above the capacitance C0 needed to produce maximum current. The capacitor is now adjusted to a value of C0 and an added series resistance of 75 ohm is found to reduce the current to previous value of I. Find values of L and R.
Yes. So let the two values of capacitance which produce the same current be C1 and C2. Okay. So this is given in the problem. This is given in the problem. This is C1 and C2. What is your C1? What is your C2? It's given. Now, you should know that what is the capacitance during required for resonance. Okay. So let the capacitance required for resonance be C0. And the formula we can have for that is C1 by C2 divided by 2. So I think it is 45 plus 37 divided by 2. It's 41 picofarad. Okay. Now at inductance, sorry, resonance, you have a formula for inductance. What is that? At resonance, there is a formula for inductance L. What is that? 1 by 4 pi square F square C0. This is the formula. So if you now put the values of F, our frequency is what? Frequency is somehow 3 megahertz. It is also given. So if you put the values here, tell me the value of inductance. It will be 4 pi square. F is 3 into 10 to the power 6 whole square. Okay. Multiplied by C0. C0 is the capacitance required, that is during resonance. That will be 41 multiplied by 10 to the power minus 12 hertz. Okay. So this is your thing. So what is the answer you're getting? Please tell me the answer. Tell me solve it out and please tell me the answer.
Ma'am, 0.68 micro Henry.
Sure. My answer is 69.2 microhenry. एक बार ठीक से calculation करो. I think calculation में कुछ problem हुआ होगा. So this is the way how you can find the inductance. Okay. Now when the capacitance, yes, Rajkumar, tell me.
If I round it, then 69.2.
Okay. 60, yes, round off. You have to take the round off. In measurement, any problem you do now, you have to do the round off. Okay. Then you see when the capacitance in the circuit is C1, you have to see that C1, which I told you, 45 picofarad. Okay. So you have to find the value of current that is flowing in the circuit. So for that, the value of current we need to find out for finding out the resistance. So this formula is somehow E divided by root over, okay, R squared plus omega L minus 1 by omega C1 whole square. Now see, in this particular equation, you don't know what is E. So you keep it E just like this. But you know all the values of this. So here you have to write R square, okay, R square plus, that is this omega L. Omega L means what? 2 pi F, 2 pi FL. So 2 pi F is 3 into 10 to the power 6, and your L is 69.2 into 10 to the power minus 6. Okay, minus what? 1 by omega, omega C1. Okay, so 1 by omega C1 means 2 pi F C1. So 2 pi F is 3 into 10 to the power 6 into C1 is 45 into 10 to the power minus 12. Okay, so this you can take whole square of it. This was the whole square. So if you solve this, can you solve it? Can you solve it? You will get something E by R plus something you will get. I equals to E by this value. Kindly solve this. E value you don't know right now. Okay, E value you don't know, so keep it. We will tell you. Okay. Acha, one more thing. Keep it like this. This is you keep it as equation 1. Okay. Don't do the solution just now. Keep it as equation 1. You will equate two things. Acha, if you have the problem, read the last line of the problem. The capacitor is now adjusted to a value of C0 and an added series of resistance 75 ohm is found. Okay, to reduce the current to previous value of I. So from this line, we can have another value for the current. That is, if I go to the next page, then at resonance, I can write my I is equal to E by R plus 75. Can I write this equation from the last statement of the problem? Now, I got two values of current. Okay, one is with the added series resistance, another is the normal current in the whole circuit. Now what you will do, you will equate equation 1 and equation 2, and if you equate, just a second, yes, and if you equate, then what will happen? E will get cut out. Okay, E will get cut out. Okay, E will get cut out. Now, my previous equation is this one. If you have written, then if you equate this equation with E by R plus 75, then from there you tell me what is the value of R. So, in that case, equating this is, that means E by R plus 75 will be equal to E divided by the whole thing, R square plus 2 pi 3 into 10 to the power 6, 69.2, 10 to the power minus 6 multiplied by 1 by 2 pi into 3 into 10 to the power 6 into 45 into 10 to the power minus 12 whole square. Okay. So now what you do, you just equate it. So this E will cut out and you will easily can find out R. Now tell me the value of R. Do the calculation, please. What is the answer? What is the answer? Solve it and tell me. Done. Big calculation. Tell me the answer. I have already done it. I'm waiting for your answer. Yes, what is the answer? Done it. Hello? Hello? Am I audible? Hello? Rajkumar, Monica, Ayushi? Hello? Why you people don't answer? Hello?
Yes, ma'am, you are audible.
Okay, tell me the answer. Simple sa calculation, you're taking a lot of time. It will somehow around 70.8 something. Somehow around that kind of. 70.8. Oh, that much. This kind of answer will come. Okay. So do the calculation at your home. Now we will shift to the next topic of our module. I think this is visible to everyone, this diagram. Okay. Now this is a diagram of, we will start with the topic, vector impedance, vector meter. Okay. Or in short, we can say it is at, this is the vector impedance meter. I'm writing here. This is called vector impedance meter. Okay. So this is the vector impedance meter. And here now see this total figure, you can see there are a lot of devices added. So measurement, now first question comes, why we use vector impedance meter? Okay, so why we use vector impedance meter? Specifically, measurement of impedance is concerned with both the magnitude as well as phase angle of a component. So here we mainly use this meter to measure the impedance. Okay. Now, in many applications, it is not only necessary to determine the magnitude of impedance, but is also important to find out the reactance to the resistance as well as inductance is also there. Now, measurement of voltage and current is usually sufficient to determine the magnitude of impedance at various frequencies. But various frequencies, that is also having a limit. The frequency range should be, the F should be less than 100 megahertz. Okay, megahertz. Now, the phase difference between the voltage waveform and current waveform, that we have to check that whether your component is inductive or capacitive. Now, from that thing, you can easily determine the phase angle. Okay. Now, CRO is somehow connected to this portion because phase angle we can determine by using CRO. And Lissajous pattern, I think if you are aware of this pattern, Lissajous SSA, J or US, Lissajous pattern, which we sometimes obtain in CRO, there is a specific condition to obtain this pattern in CRO. So that this pattern actually help in determining the reactance. Okay. Now these measurements are highly useful with the help of this vector impedance meter, and it's important. So all the devices, components we have to see. So now with development of this instrument, it is now possible to simplify impedance measurement over a wide range. So vector impedance meter, makes it possible to obtain what? To obtain sweep frequency. Okay, sweep frequency of impedance and phase angle. Okay, so typical vector impedance meter, it's used for measurement of impedance and phase angle for a frequency range, you can say 5 hertz. Okay, 5 hertz. Like this, 5 hertz to 500 kilohertz. So this is the actual frequency range. So unknown component is simply connected here across the input terminal that we will see here, and 2 meters are connected also to measure the magnitude of the impedance and phase angle. Now the operation of this vector impedance we will understood here with the help of this block diagram. 2 measurements are made here. One is magnitude, second is phase angle. So what are the 2 measurements? One is magnitude of impedance. Okay, and second is phase angle. These are the 2 important things we will measure with the help of this vector impedance meter. Now in this block diagram, what you can see, just you can tell me. See, first of all, this is a combination of many things. If you can see here, here we have used a Wien bridge oscillator, we have used a differential amplifier, then we have used this phase angle meter, Schmitt trigger, everything we have used here. So magnitude of impedance that we need to measure is done here by measuring the current that is flowing through the unknown component. Okay, when the known voltage is or when the voltage, we know what voltage is flowing through it, and phase angle is determined by finding the phase difference between the voltage across the component and current through the component. Okay, so these are the 2 things. So voltage and current plays a very important role here. Now in this particular picture, if you see here, let me tell you what is the specific meter that contains a signal source. So this is the meter that contains a signal source, is the Wien bridge oscillator. Okay, so meter which contains the signal source, that is the Wien bridge oscillator, and they have a front panel control with their various frequency and all that is adjusted. Now the output of the Wien bridge oscillator is fed to what? You can see in this picture, is fed to what? AGC amplifier. Okay, AGC is a special kind of amplifier with a feedback, it's written. AGC amplifier, which helps in what? Which helps in permit accurate gain, okay, of the oscillator with the help of any feedback voltage. Now this gain, whatever is adjusted, that is by the internal control, everything, that setting is mainly done by this AGC amplifier. Now, AGC amplifier output is connected to what? AGC amplifier output is connected to this switch assembly you can see here. It's called Z magnitude range switch assembly. Now, switch assembly, why? Because it is used as a precision attenuator network. Means to understand very precise output of the AGC amplifier. So we have used this range of switch, which is somehow called Z magnitude range switch. Okay, so a special kind of circuit is there in the switch. Now there are two modes in which impedance switch can operate. What are the two modes? One is constant current mode, another is constant voltage mode. Okay, so these are two modes. So in constant current mode, unknown impedance will be connected across the input of the AC differential amplifier. So what is the AC differential amplifier? Here you see in this picture. So this is the AC differential amplifier whose input is this thing, whose input is connected to the constant current mode of this switch assembly. Okay, so current supplied to the unknown impedance depends upon what kind of range of switch we are using, and this current is then used for further purpose. Now it's come to next what happened. You can see here. Wait. Now this current is then held constant, or accordingly we can change it. Now another amplifier is there. You can see here trans resistance. See in the downward portion, trans resistance amplifier. What is this amplifier? It's a special kind of amplifier. It's a op-amp, you can say, operational amplifier. Okay, where the output voltage is proportional to the input current. So output here you can see it's the RT amplifier written here. So the output of the RT amplifier is fed to the detector circuit and then compared accordingly to get the output. Okay, and the result that we will get, that will be definitely regulate the gain of this AGC amplifier and also that voltage applied to the switch assembly for further process. Now output of this AC differential amplifier, come to this. This is the output. This is the output of the AC differential amplifier. Where it is going? It is applied to an amplifier and filter section. See, here I have applied the output of this AC differential amplifier to the amplifier and the bandpass filter. Okay, which contains many high and low band filter and which are changed accordingly with the frequency range. So the output of the bandpass filter now connected to a detector which drives this schemic trigger. You can see the output of this bandpass filter is connected to schemic trigger. Okay, and then output of the schemic trigger is again connected to a multivibrator, then to the differential amplifier. Okay, so since the current through the unknown impedance we have kept constant, that is by this RT amplifier, you can see here the schemic trigger is also playing a very important role in handling the output of the filter. Okay, so you see here, yeah, this is the unknown impedance which I'm talking about. Okay, which is unknown to us. And one more thing you see here, another thing, Z magnitude meter. This one I forgot to explain. Z magnitude meter. So output of the bandpass filter is also connected to the Z magnitude meter, which measures what? Which measures the voltage across the unknown impedance. Okay, and then it is calibrated accordingly to give the result. So this magnitude, Z magnitude meter, is important to detect, and see it is connected with the active detector also. Okay, so you can detect the value very easily. Now, when the instrument is operating, this all thing we told you, I told you, when the instrument is operating in a constant current mode. Now, when the instrument is operating in a constant voltage mode, what will happen? Two inputs of the differential amplifier are switched. How? You see here, two inputs of the differential amplifier are switched. Now, terminal which are connected to the input of the trans resistance amplifier. See here, where is the trans? This is the trans resist amplifier. You see here in trans resist amplifier, one of the input is grounded. Have you seen? One of the input is grounded. So, and which one is grounded? This is connected to constant current mode. This is constant current mode. This is grounded in case of when we are talking about constant voltage mode. So other input of the differential amplifier is connected to the voltage terminal that you can see here, connected to the unknown impedance also. And the voltage terminal then will give the result depending upon what kind of Z magnitude, switches, ranges we are using, that will give rise to the result. Now, in case the voltage if across the unknown is kept constant, then what will happen? The current through the unknown impedance, okay, is applied to this trans resistance amplifier, which will again produce an output that will be proportional to the input current. Okay, so all these devices are interconnected with each other, and mainly they do operation in two phases. One is constant voltage mode, one is constant current mode, as I told you. Now, the role of the AC differential amplifier, see here is an AC differential amplifier, and this trans resistance amplifier are now reversed. In case of constant voltage mode, their functions are reversed. Okay, so output voltage, the voltage output of the RT amplifier now will be applied to the detector and then to the Z magnitude meter. And the output voltage of the differential amplifier now control the gain of this AGC amplifier. Okay, in the same manner as it did in the constant current mode. Only what will happen? The functions will just get vice versa or just get reversed. So these things we all did for finding out the unknown impedance in this particular circuit. Now the thing which is left, that is the phase measurement. The phase measurement, how it can be done? See here, just at the down portion, you can see at the down you see just below this RT amplifier, a phase angle meter is connected. So this phase angle meter plays a very important role, and also this schematic trigger also plays an important role. So these measurements are carried out simultaneously, okay, along with this measurement of the magnitude of the impedance. So output of both the voltage channel and current channel, they are amplified and they are connected to the what? Schematic trigger, you can see here. Now this schematic trigger circuit produces a positive spike every time that the input sine waves are produced. So this positive spikes, they have a binary phase 0, 1, that kind of structure. And then you see the output of the schematic trigger is connected to a bistable multivibrator. So what is that? You can say a bistable multivibrator, differential amplifier, and integrating capacitor. See, three things are combined here. Okay, differential amplifier, bistable multivibrator, integrating capacitor. The three act together as a what? As a phase detector. So because we need here phase angle. So these three together work as a phase detector. Okay, phase detector. And so we can say that the positive going pulse from the constant current, they set the multivibrator, because in multivibrator you will be having two conditions, set and reset. And then the pulse from the constant voltage channel, it will reset the multivibrator. So set the multivibrator, which thing? Constant current channel. And reset the multivibrator, constant voltage channel. Okay, remember these two things. Now, set time of the multivibrator is therefore we have to decide from the voltage waveform and the current waveform. Okay, set and reset, these are the outputs of the multivibrator, and which is now applied to the differential amplifier. See here in this particular picture, all the output of the multivibrator is given to the differential amplifier, which then again applied to the integrating capacitor connected, which is grounded somehow. So capacitor voltage now is directly proportional to the whatever output to the phase angle meter. See, here a phase angle meter is connected. So this phase angle meter indicates a phase difference between the voltage and the current waveforms in degrees or anything. So it's a bit complicated meter, vector impedance meter. So through this vector impedance meter, we measure magnitude of impedance and phase angle. Okay, when we are measuring magnitude of impedance, we go with a Wien bridge oscillator, AGC amplifier, and there again we shift to two methods: constant voltage method, constant current method. Okay, so those things you have to learn. And in phase angle measurement, you need a phase angle meter, which is connected with a Schmitt trigger, bistable multivibrator, differential amplifier, and integrating capacitor. So once you chalk out this total picture, you can easily write everything on your own. That how, see the connection, if you remember, I mean, this connection, you have to remember that this is the connection of the thing and how is the thing is going on. So thing you can write on your own. If in exam, if this kind of question comes that explain vector impedance meter. Okay, so a bit complicated diagram, I know, but still if you go through this once and whatever I have told you, I will give the notes to you, so don't worry. So just go through the diagram once, that where we require trans resistance amplifier, where we require AC differential amplifier, all these things. Okay. The operation of this vector impedance meter is bit large. So this is specifically in your syllabus. Only this vector impedance meter as a single topic. The single topic is in your syllabus. Okay, so I will provide the operation of this vector impedance meter as a Word file to you. Go through that matching with this diagram, or listen to the video once when what I have explained. You will surely able to understand. Okay, so if anybody, how many students are there today? 8. So everybody has given the QR code attendance. Wait, if not, let me once share. This will not come in your this exam. Okay, this portions I have not given so much in your midterm. Midterm will be on basis of mainly bridges and the first chapter which I taught you, limiting error, relative error, all those things. Okay, so give the attendance and thank you for being in the class. I will upload this video and the notes also. Don't worry. Okay, thank you so much.
Thank you, ma'am.